Okay, so in this problem, first of all, it says that we have a normal distribution, so we already know we're going to have that shape to begin with. And it says we have a population mean of 2 and a population standard deviation of 0.1. So in part A, it just says find the probability that a machine dispenses more than 2.1. And we're going to label the graph and show our calculations. So this is just, it's just asking, there's no sample. So this is a straight normal distribution problem, kind of like we had on the first exam. So I'm going to draw my curve. It's a distribution of x's with a mean of 2 and a standard deviation of 0.1. And we want to find above 2.1. So we'll just locate a 2.1 up here. And we're looking above. So we're going to find how many standard deviations above the mean we are. Of course, you can probably see it's 1. But I'm going to go ahead and write the formula and all that. It's z is equal to x minus the population mean over the standard deviation. That's 2.1 minus 2 over 0.1. And that comes out to equal 1. And when you have a z of 1, you can look in your z table. You'll find 0.3413. And that's going to be the area from the mean to the point we're at. And of course, we're looking above there. So that's going to be 0.5 minus the 0.3413, or 0.1587. And so all of that is part A. Okay. Part B, we have a sample of size 4. So we're going to use it 4 times now, and we're finding the probability that the sample mean is more than 2.1. So it's going to look a lot like part A, except we're going to adjust the standard error. We're going to divide that sigma divided by the square root of n, and then the symbols will change a little bit, but the process is exactly the same. So over here we'll have for part B, okay. Thank you. I'll pause for a second here. Okay, I think I'm recording again, but here's the really good thing is it could come back right in the middle. So I'm still going to work over on the other side.
Go back or like undo. Okay, there is no undo.
Okay, I'm going to work this part, and then I'll pause again. Okay, so again, n is equal to 4. We're asking about sample means, and more than 2.1. So since it's asking about sample means, the sampling distribution should have x bar over here. It's asking about sample means. Since the population is a bell curve, this is automatically a bell curve. We don't need the 15, 40, 100 stuff. This is already a normal distribution for the population. So this is automatically. Now the mean of this distribution, all this mean is the mean of the sample means. So that's the distribution, is equal to the mean of the population. So that's still 2. But it's narrower because we have a sampling distribution. So the standard error is going to equal the population standard deviation divided by the square root of n, which is our 0.1 divided by the square root of 4. And that's going to be 0.05.
That also goes back to the Z table.
Right. This, when you're doing all the sampling distribution problems and we have the bell curve, this is going to be a Z. In fact, anytime you see the symbol sigma, you're going for a Z distribution. The T is only when you have a sample standard deviation. So remember, when we worked over here, we had Z was equal to X minus mu over sigma. Well, this has that same form except for it's, I want to put this over here, Z is equal to X bar minus the mean of the X bars over the standard error of the X bars. So when it's asking for sample means, everything changes. The X goes to X bar, and the mean and the standard deviation are the mean of the X bars and the standard error of the X bars. So we're asking greater than 2.1. So we've still got 2.1 over here, but this time it's an X bar. And we're looking for this area right here. So the X bar we're asking about is 2.1, then minus the mean divided by 0.05, and that comes out to be 2. So Z is equal to 2. And if you look up for 2.00 on your Z table, you're going to find 0.4772. And again, that's this area here, 4772. So the area in the tail then will be 0.5 minus 0.4772, which is 0.0228. So just rehashing. It tells you in the first part you had a normal distribution. It gave you a population mean and a population standard deviation. And it's asking to find a probability. So we're just finding a probability. And we aren't doing HO and HR or anything like that. We're just finding a probability. And so in that first one, no sample was taken, and we're just finding the probability that X is somewhere. So that was just, you already have this in your notes, but it's just X here, mu, and sigma, and we're looking for that area out there for X's. In part 2, we've used it 4 times. Usually it'll say in a random sample of this many, but that still is just 4 times. And it's asking, we're still finding the probability, but we're looking for the probability of a sample mean. So if it's asking about sample means, the distribution is a distribution of sample means, which via the central limit theorem will be a bell curve. In this case, if the population is normal, any sample size will do. It'll be a bell curve. It would just be, if we drew these to scale, narrower. Okay. Sampling means kind of what you mean by central. It pulls it into the center. And, you know, the main thing is numerically. The main numerical difference between the two problems involves correcting the standard error. Taking that population, in part B, Part A, you just use the population standard deviation 0.1. In Part B, you have to correct the standard error by taking that population standard deviation and dividing by the square root of n.
Now, you would use, because it's a normally distributed population, you would use
Both of these involve the Z table, yes. So when I looked up in the other one, I had Z is equal to 1. I just went to 1.0 on there, and I saw 3413. And in this second part, I came up with a Z of 2, so I just went down to 2.0. Remember, that's always from the mean to some point. That's this area, but I shaded in what I'm looking for, and it's out here. So, I know from there up is 0.5, and so I just need to subtract.
So every time it says sample mean, it's always going to be an X bar.
When we're finding the probability of the sample mean, yes. Well, anytime in anything it says sample mean is X bar. Population mu, population standard deviation sigma, sample standard deviation S.
So for probabilities, this is when we...
These are the only two that we're going to do for probabilities. They're always going to be Z's.
Okay.
So when we're computing probabilities, at least, in this class, well, I take that back. Earlier, we did binomial probabilities, but that's a whole different deal, and that's not going to be coming up on this thing. Okay. Other questions about this one before I... Okay, on this one, we have, okay, there's a typo in there. In fact, there's two typos on there. I'm counting 16 in each one of those. So, first thing we need to do is fix that. I knew the first one was wrong because I know that's not 1. There are 16 here, 16 values. And there are, it should say, if I counted right just now, that's also a 16 right there. So we have two types of cars here. And we just want to know if type A, can we be confident type A has higher gas mileage than type B? So if we were writing this as a hypothesis, as asked in Part A, HR would be mu A greater than mu B. HO would be mu A equal to mu B. So it says here we're going to use our calculator to compute the 95% confidence interval. So what we also know is we're going to compute that confidence interval. A couple of things. A, it's two separate samples. So this is going to be a two-sample T interval. If we were doing a test, it would be two-sample T test. So we know it's two separate samples. This isn't, any kind of matching or anything. These are two. We have 15 type A cars and a separate 15 type B cars. We didn't, in this case, we didn't say take one car and drive it so far with A and then so far with B, then take a separate car and do it with A and B. That would be matched pairs. This is two separate samples, an independent random sample, separate sample. Okay. So if we were going to do this by hand, we would have to compute X bar for both groups and the variance or standard deviation for both groups and so on. That's okay. I'm going to go back through things, and I'm expecting some people not to show up until 6.
Okay.
So,
The class, management class, and if you register the spring 2013, it tends to on that class
okay. So we're looking at problem 2 right now. So I'll work through all of these problems, and then, I'll turn the recorder off, and then work more on the board as well. Okay, so anyway, on number 2, there are 2 separate groups of cars. One sample of size that should have said 16, and then another one of 16. Wasn't 1 and 15. At least if my counting was right a minute ago, there are 16 in each group. It said, can we be confident that A-type automobiles have higher gas mileage than type B? So mu A greater than mu B for the hypothesis. What we'll need to do now is go into our calculators, and in lists 1 and 2, or wherever you want to put them, just enter the numbers from this problem. Hopefully on the exam I won't give you one with this many numbers, but we're looking at number 2 now.
Oh, I got it.
This is the one, the review thing I put out there. Okay, so I have all the numbers in here. I don't do the L2 minus L1 stuff because these are 2 separate groups. Okay? And it says independent random sample, means it's just a separate group. So now you can do stat, test, and we're going to do an interval, so we're going to go down to 2 sample T interval. And you can input the data, and mine says list 1 and list 2, and we want a 95% confidence interval. So do we pool or not? I'm going to make a guess right now, and we'll see if I'm right in a minute. I'm going to guess that neither variance is twice the other, because it looks like all these numbers within each one are pretty close. I could be wrong. We can check that out in a minute. But for now, I'm going to select yes on the pooled and hit calculate. And I can look, for one thing, at those 2 standard deviations. One of them is 1.67 and one of them is 1.63. I'm reasonably confident if I double those, neither is going to be twice the other. They're going to be really close to one another. So I guess right on the pooling. Stat, test, 2 sample T interval. 2 sample T interval. And did you guys get 0.3692 for the first one? I didn't check to see if I entered my numbers correctly.
We're guessing it's full number, yes.
Yes.
Because neither of them are twice.
Right. I'll write it down here in a second so we can be more formal about that. But I want to know if anybody else got 3692 or if I need to go check my numbers. You got the same thing? Good. So for part B, I have 0.3692. 2.692, and then I 2.7558. And if you're working something where I just tell you to use your calculator, please use, on the confidence interval, all the decimals that they use. Okay. So that would be B. That's just it. Put the interval in. And based on that interval, can I conclude or be confident type A has better gas mileage than type B? Yes, because the entire interval is greater than 0. Okay. So C would just be yes, entire interval is greater than 0. And that'll take care of part C. What graphs would you draw for this? Okay, I would draw a box plot. Actually, it would be a multiple box plot. You'd have a box plot for A and B. And what would you be looking for in those box plots? Okay, one of the things I want to do is look for outliers. Because these sample sizes are 16, I can handle skew. I'll look at those box plots. If there are any outliers or extreme values, that will call this analysis into question. So that's one thing I would look for is outliers. What else would I look for in the box plots? Outliers and extreme values. Since I have two box plots that are on the same scale, I'm just going to visually look at it to see if it looks like there's a difference between the means. So I've had my numerical things and everything, so I'm just making these up. If I had box plots that look like that, that looks to me like they're pretty close to the same. Whereas if I had box plots like this, it looks to me like the second group, the one that I have on the right here, has a higher mean. Although in this case, since I know the first one's larger than the second one, it probably would have looked something like where you can see fairly clearly that one of the groups is a little bit higher on the scale than the other one. So the graphs I would draw for this are, at the very minimum, a box plot to look for outliers and extreme values, and also just to get a comparison of the groups. So when you're working on your projects and things, you're drawing graphs, the things you ought to look at when you're having your box plots is, A, what does this tell us about, do we have a large enough sample? And then B, just to look to see if there are obvious differences between the two, and just what it looks like. I mean, a picture is worth a few words and numbers. I know 1,000 words, but maybe 2,000 numbers sometimes. Okay, so I want to come back and do just a couple of other things on this. When we put this in our calculator, I had the standard deviation for I'll just put the standard deviation for group A was 1.67. And the standard deviation for group B was equal to 1.63. Now I want to know if I'm going to pool or not. I would need to square those. Okay, so S squared A is equal to 1.67 squared. Just 2.79 about. And S squared B would be equal to 1.63 squared. So about 2.66. Since neither of those is twice the other, we should pool. Or if you're using your calculator, you answer yes. Okay. The other thing, I'll have to run through this again. On this, I'm going to note I had X bar for this group came out to be 32, and X bar B came out to be 30. I'm going to round that to 4. So in this one, I had all the numbers. I just put them into list 1s and list 2. Remember, it's not matched. It's two separate groups. So I just ran 2 sample t interval and referred to list 1 and list 2. You could have a problem where I said, here are, in a random sample of 16 from group A, I had a sample mean of 32 and a sample standard deviation of 1.67. In an independent random sample of 16 B types, I had a sample mean of 30.44 and a sample standard deviation of 1.63. Now construct the confidence interval and so on. In that case, you would have X bar A minus X bar B. I'm just going to write this on the board. I've got too much on there. You would have X bar A minus X bar B plus or minus a t value. It's t because we have sample standard deviations times the standard error. And since it's pooled, it would be that relatively big formula, the S squared A NA minus 1 plus S squared B NB minus 1 over NA plus NB minus 2, all of that times 1 over NA plus 1 over NB. And the degrees of freedom for that T would be NA plus NB minus 2, or 16 plus 16 minus 2 is 30. I'm not going to work all of this out, but I'm going to go ahead and just set up the formula here. So we would have X bar A minus X bar B, which is 32 minus 30.44, plus or minus, we want to get a t value for 95%, is it 90 or 95? 95% confidence and 30 degrees of freedom. That's 2.042, just reading that off of the t table. And then when I put into this formula, I'm going to put the variances, the ones that I squared, the 2.79 times NA minus 1. I'm just going to put 15 there. Plus, then the 2.66 times 15. All of that over NA plus NB minus 2, which is 30. And then 1 over 16 plus 1 over 16. If you were to calculate all of that out, you should get very close to what we had with the calculator. just did all that math, you'll get it'll be a little bit different because I did some rounding on the 30.44 and so on, but you should get pretty close to that interval. So let me ask you guys, what questions do you have about this kind of problem?
Could you say, I can't remember the way, could you say one more time how you tell if you would do either that or...
In this case, it just said use your calculator. Okay. All this, that's just the formula that the calculator is using, so I just went ahead and wrote that over there. But okay, the decisions you have to make are, if you see two columns of numbers like this, the first thing you need to know is this matched or independent or two separate groups? Okay. In this case, it says independent random sample. It's two separate groups. It would be matched if I said I drove one car. Well, there's no way this one could be matched. Here's an example of something that could be matched. If I had type A gasoline and type B gasoline, and if each row on that was one car. So the first car got 31 miles per gallon with this gas and 32 with that one, but each row is just one observation. Every number on here, this is 16 type A cars, and of course they're not the same cars as the 16 B cars. So these are, when I look at one row of this right here, when I look at these two numbers, the 31 and the 32, is that the same person or the same car? It's not. Those are two different cars. It's separate groups. If those were two measures on one car, it would be matched. So once I know it's an independent samples group, then the next decision is pooled or unpooled. Now, when we ran through it the first time, I put all of those numbers in type A into one column, list 1, and all the ones from type B into list B, and I just went stat, test, to sample T interval, and referred back to those two lists. I selected yes or pooled the first time, knowing that I might have to come back and change it, but I selected that because it looked like to me that both of the groups had about the same amount of spread. And there any, like, if one of the groups was everything in the low 30s, high 20s, and the other one was ranging from like 15 to 50, I would have thought, oh, they have different standard deviations and different variances. So I did that, and when I did the confidence interval, it did give me the standard deviations, and I square those and found, in fact, that neither variance was twice the other. Therefore, you pool. And so all I wrote on the board was, if we didn't have all of the numbers there and I just gave you the means and the standard deviations, that's the formula you would use. Other questions on this one?
If it was a match pairs, that's whenever you had to find, or you would either give us the means.
Well, on a matched pairs, we'll tend to have the prototypical example would be before and after. So, for example, let's say that you took a test over exam 2, maybe, I don't know, a week and a half ago or so, and you got a score, maybe you've made a 44. I'm not saying that you made a 44, okay? I'm just saying maybe you could have been one of those people that made a 44. That might have been, no, I'm just kidding. That might have been a pretty good score. But let's say that now you're going to take the exam again, and you make a 94. X then is 50 points. That's how much you improved. So I do that for everybody in here. I've got their tests first time, their test second time, but really what I'm interested in this case is how much did you improve? And if I can't show that there's improvement, then I should stop doing this because, it takes extra time to grade it and everything. So, I should test that hypothesis. And if it doesn't come out, then I should stop doing it. I assure you that they will go up on average. I think I can be pretty confident in that statement. Unless this is like the worst group ever. I'm just kidding. So that's what, now the independent, like this one would be, The people on that side of the room are group A. I'm only getting one measure for each one of those, like type A cars. Help. And then the people on this side of the room would be type B. So now if I were doing in test scores, I would want to know what I would be testing. Are the people on the left side of the room, do they score higher or different from the people on the right side of the room? But two separate groups. Let's take a look then at number 3. I'm actually just going to move way up here a bit. I think what I'll do... That's not what I want to do. So we'll get part of this at a time. So in this question, in this particular problem, I have 3 fonts, and I want to know, I think, how long it takes to read a passage depending on the font. This is really similar to a project that some students in this class did a few years ago. Instead of using different types of font, they used different sizes of font. And what they didn't tell people that they were looking at how fast they read it. They said, this is sort of like having a blind or a double blind kind of thing. They said, I want you to read this passage and I'm going to give you a quiz on it afterwards. And then they kind of looked at their watches and recorded how long it took them to read. So this might be for different fonts. How long did it take them to read it, and what were the standard deviations, and so on. But the key is we're looking at means, and there are 3 groups. That makes this an analysis of variance problem. Okay? 3 means, 3 groups. The research hypothesis is going to be the research hypothesis is going to be that there's at least one difference between population means. That should be an R there. So at least one of the following is true. Mu A not equal to mu B, mu A not equal to mu C, mu B not equal to mu C. And HR would be that mu A is equal to mu B, is equal to mu C. So the hypothesis on Anova, always exactly the same. At least one difference between pairs of population means. They're all equal. And I'll only give you the 3 sample case, so it's going to be just exactly like this. Then to test the hypothesis, we're going to reject HO if F test is greater than some value. I'm going to write that up here. Maybe not. I guess I'll write it down here. Reject HO if F test is greater than some value. And so we'll need 2 sets of degrees of freedom for this. For the numerator, it's going to be k minus 1. where K is the number of groups. There are 3. Minus 1, that's equal to 2. And then for the denominator, it's going to be the total sample size which I'll call NT, just total sample size, minus K. And the total sample size, we had 8, 8, and 8, for a total sample size of 24. So 24 minus 3 is equal to 21. So just find the F table. And for 2 and 21 degrees of freedom, it's 3.5. So we're going to reject HO if F test is greater than 3.5. The F test is going to equal MSE, mean squared error. I'm sorry, mean squared treatment. So that should be MSTR, sorry about that, divided by MSE. I was wanting to calculate MSE first because it's easy, and so I jumped ahead there. So what do I need to do to get MSE? And that's going to be to get MSTR. We'll need to get the grand mean. I want to get the mean. I'm getting the denominator first, the MSE. You have your formula sheets. If you don't, that's okay. But if you did, that would be kind of handy for you to have. MSE is equal to the average of the 3 variances. So the first thing I'm going to have to do is I'm going to take these 3 standard deviations over here and square them. So I'm going to get S squared A, S squared B, and S squared C, and then take the average of those. So I'm going to take 12.86 squared, and that's about 165.4. And then I'm going to take 10.29 squared. That's 105.9. And then I'm going to take 11.28 squared. And that's about 127.2. I know I'm going to need some room down here for mean square treatment, so I'm going to try and do this up here. MSE is equal to S squared A plus S squared B plus S squared C, all divided by K. So 165.4 plus 105.9 plus 127.2, all divided by 3. $132.8. Other people are getting that too? So 132.8. And that'll be then my denominator. Well, maybe I did it. This thing doesn't like, I don't know if you guys can see this, but sometimes I'm writing and I have to go back over it because, yeah. That's also why I write in cursive sometimes, because when you lift it up, there's a delay before it'll start picking it up again. Sometimes. Okay, so now I need to get the mean square treatment. And you're right, the first thing on that is to get the mean of the means. So I'm just going to get that right here. X bar bar, the grand mean, is equal to X bar A plus X bar B plus X bar C divided by K. And so that's equal to 54 plus 44 plus 67 divided by 3. And I got that to be 55. And then the mean square treatment remember, this is sort of like getting how far apart are the sample means. And when we did a t-test, we could just do X bar A minus X bar B. This is sort of like that, but we're subtracting all three means from the overall mean to see how far apart they are. So I'll have the sample size for the first group, X bar A minus X bar bar squared, and then just keep that going with NB X bar B minus X bar bar squared plus, and then for the third group, and all of that gets divided by K minus 1. So now we have 8, 54 minus 55 squared plus 8, 44 minus 55 squared plus 8, 67 minus 55 squared. All that's going to go over 2. Let's see, this first term, let's see, 1 squared times 8. I'm going to get that one in my head. That's 8. And then we're going to have 11 squared. That's 121 times 8. So that's 968. And then I'm going to have 12 squared, 144 times 8. It's 1152. And all of that's going to be divided by 2. Are you guys getting the same numbers I'm getting? So I get 1064. And that's my MSTR. 1064. And then I'm going to divide that by MSC, 132.8. I got 8.01. I know I've got a lot of stuff up here. Reject HO if F test is greater than 3.5. it's 8.01. That's greater than 3.5. So reject HO and conclude that at least one of those is true. Okay. Just as far as I've gotten to right here. Questions? This 2 here? That's K minus 1. K is the number of groups, and there's 1, 2, 3 groups. Okay.
And it's only going to be the test.
Always the one-tailed upper test for both the F test, and no, it's not on this test. The next one, the chi-square test, also is always reject HO if F test greater than. Okay. For the numerator, for the degrees of freedom from the numerator, it's K minus 1, where K is the number of groups, 3 groups, Colibri, Comet, Sans MS, and times New Roman, 3 groups minus 1. And then for the denominator, it's the total sample size minus K. So we're going to know K is 3, that's the number of groups. And the total sample size is, I had 8 in each group, so the total sample size is 24. 8, 8, 8. And so then I use those 2 degrees of freedom, the 2 and the 21, to look up in the table the critical value 3.5. Make sure you square those standard deviations to get variances before you get MSE. Okay. Other questions before I move down here? I love it. This thing works differently every time I use it. It's great. Well, it's okay. Okay, so I'm just going to fill in this table. Now, part of this you guys may have to help me because I don't remember everything. I do remember that the F test was 8.01. This part stays the same. The other part, the one part that does stay the same is, I forget to do this every time to come back and change this. Okay, so the F test was 8.01. If I remember right, the mean square for the treatment was 1064. Right. Was MSE 132.8? And the degrees of freedom were 2 and 21. Those things you should just be able to fill in from everything that's there. And I'd be, at this point, kind of, well, not thrilled, but at least I'd be okay with if you got that far. So to get the sum of squares, see, this is the mean of it, and the degrees of freedom are what would be in the denominator. So if I want to get the sum of squares for treatment 2 times 1064, it would have been the same as the numerator when I calculated that, or 2128. And then for the error, it'd be 132.8 times the 21, or 2788.8. That doesn't look like something we calculated. It's because there's more than one way to calculate MSE. If you're calculating MSE and you have the variances, the way I did it's a lot easier. This would be if you just had the whole data set, all 24 numbers, and computed one variance for all of those. This would have been the numerator for that. And if you read through the Roach approach stuff, I do work one of them out like that. But actually, usually what I do is MSE the way I have it, then multiply by the degrees of freedom. Or just read it off of a calculator or a computer. Okay, so which specific pairs different from one another? We concluded before that at least one of these was true. Mu A not equal to mu B. Mu A not equal to mu C. Mu B not equal to mu C. So we've already concluded that one or more of those is true. So what we're going to look at first is, well, how far apart were the sample means? And I had sample mean for A and B was 54 and 44. So I'm going to get the absolute value of the difference between X bar A and X bar B. And that's 54 minus 44. And that's equal to 10. And then for B and C, for A and C, I'm going to have 54 minus 67. So those differed by 13. And for B and C, I have 44, 67, and that's 23. So those are just the sizes of the difference between each pair of sample means. The HSD says how far apart do the sample means have to be before I conclude that the corresponding population means are different. So HSD is equal to Q times the square root of MSE divided by the sample size of each group. The MSE, I want to skip Q for a second here, was 132.8. And NG is just the number in each group. I could have just as easily put NA or NB or NC, assuming that they're all the same, which for this test to be true they are. So that's 8. And the Q comes with some degrees of freedom. The degrees of freedom in the numerator, it's just K, which is 3. The degrees of freedom in the denominator is the same thing as it was with the F test. So for the denominator, it was total sample size minus K, or 24 minus 3 is 21. Did I see someone have a hand kind of? Okay. So then just go to your Q table for 3 and 21 degrees of freedom, and you'll see that it goes from 20 to 30. Just use the one that has the lower degrees of freedom, the one that has 20. So we'll use 3.58. Q table. Values of Q. And so we have 3 in the numerator, so go to 3. And then go down. If it had a 21, we would go to that. But always error by going up from whatever the degrees of freedom are. So I'll use 3.58. And just do a little multiplying. And I'm getting 14.6 about. And of those mean, this is how far apart do the sample means have to be before we conclude that the corresponding population means are different. So that only happens once. The 23 is the only one that's greater than 14.6, and that's for B and C. And you can see on your thing that the X bar is lower for B than it is for C. And since it's how long it took, I would suggest that to mean that if I had a choice between Comic Sans MS and Times New Roman, and I want people to read fast, I should use the Comic Sans NS. It's faster, lower time.
What did you compare your 14.6
To all of the differences between sample means. Okay, so I got the absolute value. I didn't write the formulas down every time.
to? No, you're fine.
But you can see the pattern here. I did make the calculations, the 10, the 13, and the 23. So how far apart do they need to be before you can think of each one of these as an HR. How far apart will I say this HR is true, or I'm confident that this HR is true? It's when the difference between sample means is larger than 14.6. And that only occurs for groups B and C.
How do you calculate that first column again?
This column right here? Product of those two. When we did, if you look a little bit back in your notes, if you look at the numerator, when we calculated mean square treatment, that would have been 2128. So everything except for this sum of squares errors, we computed directly when we worked out the formulas. We computed F, we computed mean square treatment, we computed mean square error, we computed the degrees of freedom for the numerator. That's where the treatment is, mean square treatment on the top, and the degrees of freedom for the error. That's what we had in the denominator. And the sum of squares treatment was the numerator in that one. The only one that we didn't calculate directly in here, if you, like I said before, if you took all of those 24 numbers, got the deviations of each one from the overall mean, squared those and added them up, it'd be 2788.8. But it's easier to say 132.8 times 21 if you have the other things already.
What if the rounding from the calculator is different? If you get it from the calculator, it's 2790. Doesn't matter?
That's just rounding. And I did, in this case, provide the actual data, too. I think on the exam that kind of freaked some of you out last week because I didn't give you the actual numbers. I just gave you the means and that kind of stuff. But I did in this one, so apparently you took the time to enter list 1, list 2, list 3, and do an Anova, L1, L2, L3. Yeah, I knew there would be some rounding in there. I'd say 2790. I'm not too bad with that. I got 2789. Yeah, if there were 2,789 pennies here, I probably wouldn't be able to look at it and say, wait, that's 27. I'm just kidding. Other questions on this one? I think all of this together, it was worth probably, I don't know, around maybe 25. Not quite. Maybe around there, 22, 24. Does anybody need a copy of this? Okay, so you can see this one has after and before. That's a matched pairs. I think the first question on here is the sample size large enough? Well, n is only 6. That means that there can't be any skew, no outliers, no extreme values. We should know or expect that the population is at least close to a normal distribution. Doesn't have to be perfectly, but close. So I think that was the first question on there was, is it large enough? Then the hypotheses. Be careful on this one. There's only one sample here. That means there's only one mean. It's not mu A and mu B. It's just one mean. Okay. So HR, and did it again. Some things you can know with certainty, and that is that, I'm going to forget every once in a while. So when you have the matched pairs, let me see, is mu greater than 0? Did it go up? And HO is mu equal to 0. The only thing you have to pay attention to is make sure that it matches your direction of subtraction. The other thing, and the reason I'm assuming here that the higher the number, the higher the score. If this was talking about how long it took them to finish the game or something like that, then lower would be better. Okay. So I'm going to do after minus before and just let that equal x. So Alan improved by 5. So this is kind of like your exam scores. They're going to go up, hopefully more than 5. I'm glad we can all have a sense of humor about that, but, hopefully there will be no need for laughter in the future. I'm not liking this. What do you guys get when you add up that column of numbers? Oh, well, there was clearly an error in the recording of numbers in this. I believe that poor Freddie, he really only made it up to, let's see, if he made it to 149, that's minus 1. Oh, no, it was 149 before. Actually, he only went down by 1 instead of 2. Am I going in the right direction? Is that going to be 24? Or did I go in the wrong direction?
That'll be 26.
Okay, so actually, it was 151. And he went down by 3. Now I'm at 24. I believe. Am I?
Yes.
Hey!
We're good at that.
Well, I can tell you one thing. I know one thing. That thing's not going to be 25. Because, I'm not going to have a sample mean coming out uneven. So, I'm going to compute the sample mean just the sum of the x's divided by n is equal to 24 divided by 6 is equal to 4. Then to get the standard deviation, I'm first going to get the deviations. This is going to be a t-test, right? So that means I'm going to need sample standard deviation. So I'm going to, in this case, have to calculate it. X sub I minus X bar. So I'm subtracting 4 from each of these. 1, 0, 8, minus 3, 1, and minus 7. And that adds to 0, so I'm thinking I must have gotten those right. You guys get 124 for that. And so the sample standard deviation sum of the squared deviations divided by n minus 1. So the square root of 124 divided by 5. It's about 4.98. I'm going to have to erase all of this off here before I have enough space. All I've done so far, I'll rewrite the hypothesis in a minute, but all I've done over here is, since it's matched pairs, since this row just represents Alan, okay, I've just got his improvement and everybody's improvement. Once I have these improvements, these numbers over here are no longer relevant for working this problem. These are the x's, and I've just computed the mean and the standard deviations of them. So on the matched pairs, find x. Now remember, we did this on the calculator. We would have put these numbers in list 1, these numbers in list 2, then went to the top of L3 and put L1 minus L2.
Is the hypothesis always going to be something equal, or greater than or equal to 0?
It is, for our purposes, it will be. You could say, can we conclude that the improvement was at least 10? But we're only going to ask about simple improvement or change. So yes, for us, always going to have 0 there. Other questions on just what's on there now?
Instead of greater than 0, less than 0.
If this had been, how long does it take to finish something? Then improvement would be that it went down. Now, the thing is, you can even make those be greater than. But the way you would say it is that you're saying that it went up because the first one was slower than the other one, which would mean it took more time. So you can always make it greater than. You just have to make sure that that's consistent with the way your data are. Here, these x's are how much the score went up. You could, the way I'm saying it is, you could let those x's be how much slower they were the first time than the second. And then you have positive numbers and you have greater than. So I would say with the greater than, it's pretty straightforward. If there were one where it's less than or with time, you kind of need to just be a little more careful in your thinking and make sure that you have them matched up.
Would it matter if we did L2 minus L1? Would it then?
If you did L2 minus L1, it's going to flip all the signs, and it's going to flip your hypothesis. Now you would say mu less than 0. What you would be saying in that sense is that my hypothesis is that the scores were lower before than after. That's the same thing as saying they're higher after than before. You just have to match the direction of them. My personal preference is always to try and make it be positive numbers the most I can. That's just a personal preference. Other questions on this part? Say again now. Oh, is the sample size large enough? We have an N of 6, so it's large enough if and only if the larger population can be assumed to be a bell curve. You could have just put no skew, no outliers, no extreme values, and I'd be okay with that in here. But you really need at least a mound shape kind of thing.
Let's say no skew, no outliers.
No extreme values. Really, a better answer is normal or near normal. So I'm just going to rewrite up here. Our research hypothesis was mu greater than 0. HO was mu equal to 0. We've computed X bar to be 4, and we've computed the sample standard deviation to be 4.98. So for the critical value approach, we're going to reject HO. If it's a t-test because we have a sample standard deviation. A problem could say it's a sample standard deviation, or in this case, we calculated the standard deviation from a sample. If you have a sample standard deviation, it's a t-test, go the same direction as HR. Our degrees of freedom is n minus 1, which is 6 minus 1, which is 5. And so let's see, we have alpha 05, one-tailed test, and t. Gosh, I hope that's not 2.015. Is it? I don't want to be memorizing any more numbers, even, on accident. I should be put out to pasture right now. Yeah. And remember, once we had this, we had our X was the before, minus, after, and this, it's just a one-sample t-test. Once you've matched it, got your X's, it's just a one-sample t-test. So the t-test is equal to the statistic, which is X bar, minus the hypothesized mean, divided by the standard error, which is SX bar. So 4 minus 0, and over here I'm going to get SX bar, it's equal to S divided by the square root of N, which is 4.98, divided by the square root of 6.
Where did 6 come from?
N. There's 6 values here, sample size. Okay, so that's 2.03. Did everybody get that? The question was, where did N come from? It's just how many are in the sample. Alan, Bonnie, Chuck, Dina, Enid, and Freddie, that's 6 people in the sample. So that's 2.03. About 1.97. And that is not greater than 2.015. So we failed to reject HO. Mu could be 0. Question on what's just up there now. Let's take a moment and just kind of review how to do this one on the calculator. Sound like a good idea. Okay, so stat, edit, and put the numbers from the problem into lists 1 and list 2. List 1, list 2. So just stat, edit. If you have some numbers in there, you can go to the top and then hit clear to bump those out. And just put those numbers. Okay, so now go up to the top of column L3. If there's anything, clear L3 out if there's anything in there first. Then go to the top of L3 and highlight the L3. Then do second 1, which is where L1 is at, minus second L2. And you'll see it writing the formula down at the bottom there. So you're going to have L1 minus L2, or second 1 minus second 2. Hit enter, and it's going to fill in those values of x that we had before. If you go back and look on the previous sheet, you should have 5, 4, 12, and so on in the numbers now. Now we're just doing a t-test, so we'll now go stat, test, t-test, option 2. And at the top, you can input either data or statistics. Well, we have the data. We also have the statistics, but let's use the data. And so select data, and then you're going to say at the top it tells your hypothesis. So that's going to be 0 on the top one. Mu 0 is 0. That's from your null hypothesis. And then tell it to look at list 3, because that's where we put the differences between L1 and L2. And then you have to put a greater than sign down there. Is there anything else? I think that's it. And then just go down and hit calculate. And you should see a t-test value that's pretty close to the one we have of 1.97. You can also have a p-value there, which I'm going to assume is probably somewhere around 06 or 07, something like that. Because I knew we were close to the 05 cutoff. Not that far off from it. You can also get a confidence interval. Okay, the confidence interval, stat, test, go down to t interval. And then just select t interval And it already should be referring to list 3. Let's say you want a 90% confidence interval. So just change the C level to 90 and then hit calculate. And what did you guys get for a number on that? The interval.
Negative 0.0967.
0.0967. Okay. The key thing about that is the interval includes 0. That means mu could be 0, that HO could be true. So like the difference between means and the difference between proportions, when you're looking at the matched pairs, because it has 0 here, you're looking to see if that interval crosses 0. If it does, then there may have been no improvement. The population mean could be 0. So other questions on this one? Yes.
Calculate a question quick. Can't get my list back to 110.
If you ever lose at the top of your calculator, where you don't have L1, L2 through L6, you have 2 options. One of them is to just ask me. Or like if that happens during a test or something. Or you can go to just hit Stat, and there's option 5 says Setup Editor. And if you just hit Enter, it'll say Setup Enter, hit Enter again, and now you have all your lists back. Okay. Other questions? I only know that because I've done it 100 times. I mean, it doesn't seem that intuitively obvious to me either. In fact, I have to admit, occasionally there's some things that it's like, even though I've done it 20 or 30 or 50 times on there, I just have to learn it new every time, you know. Okay, so number 5, doing a little quality control thing here. And we're going to recalibrate these dispensers anytime it differs from 16 ounces. So we have a sample of 10. We have a sample mean of 16.3 and a sample standard deviation of 0.08. Now, as soon as I said sample standard deviation S, that means we're doing a t-test. Okay, so can we conclude that the population mean is not, or that differs from 16? So HR is mu not equal to 16, HO mu equal to 16. So that's A. So B says to use the p-value approach to test the hypothesis using an 0.05 level of significance and using your calculator to compute the p-value. So for part B, we will reject HO. If p-value is less than 0.05 and p-value we will just get from our calculator. Okay. So stat, test, t-test, you're going to input stats now because we don't have all of the hopefully I was saying that should have been 10 up there. It didn't come out when I I think I tried to write it, but maybe not. So you're inputting statistics. Mu 0 is 16. X bar is 16.3. S is 0.08. Sample size 10. Not equal to, and calculate. Ooh. Ouch. That's really small. That's 8.51 times 10 to the minus 7th. Is that what you guys have? So that's 0.0000000, 6 zeros, and then 85. That's less than 0.05. So reject HO. And you can conclude that the population mean is not equal to 16. It's time to recalibrate this thing. I'm going to draw this not completely to scale, but I'm going to give you an idea of what the scale looks like. This is a distribution of X bars. It has a mean, whatever our hypothesis is, of 16. If you looked on here, the t value was almost 12. It was 11.86. That means that the X bar that we observed is 16 standard errors above the mean. And I know 3 is about here. 3, 6, 9, 12. So 16.3 is about there. I just know from the t value it's 12 standard errors above the mean. This is a two-tailed test. So when we're talking about this p-value, some of it's up here, and some of it is down here below 15.7. So the p-value is the stuff in the two tails. Obviously, you really can't see it on here, but it is the stuff in the two tails. So that'd be a reasonably good graph of the sampling distribution in this case, yes.
Is it 2 single p-tails?
One. There's only one sample here, n equal to 10. Just 2 tails, yes. And it's just 2 tails because HR is not equal to. Now think about this. You've got this juice dispenser. It could put in too much juice and be up here. Apparently, they're really concerned about like putting too much in here. Or maybe it's going to spill over, or maybe, well, think of it. If you have millions of bottles of juice and you're going over a little bit every time, that could be a lot of juice after a while. Or down here you could be shortchanging. What we've basically said with this hypothesis is when we can show it's not equal to 16, we're going to recalibrate this so it is 16. We wouldn't want to recalibrate if we had a value right here, because you would expect that, give a normal variation around the mean. But if we get out here, this is no longer normal random sampling, that it's just because I took this sample. Given the standard deviation and everything else with this one, that's very unusual. It wouldn't happen if it really was 16. So on the if-then thing, if this is true, if mu is equal to 16, then there is a p-value chance of getting above there, and since it's a two-tailed test, or down there. So if mu is equal to 16, then there is a 0.000 chance of either of one of those, either one of them, of either x bar greater than or equal to 16, or, and this is just because it's a two-tailed test, x bar less than or equal to 15.7. Yes, it should be. Thank you. Thanks. Greater than or equal to 16.3 or less than or equal to 15.7. Appreciate it.
How did you get the 15.7?
Okay. The distance between 16 and 16.3 is 0.3. On a two-tailed test, you go the exact same distance the other direction. So if this distance is 0.3, then I'm going to subtract 0.3 from 16. So 16 minus 0.3 is 15.7. So this distance here is 0.3. 16.3 minus 16. So this distance has to be the same distance of 0.3. It's just going in the other direction. So 16 minus 0.3. This is it. Come on in. Okay. Other questions about this problem? Okay. Well, have an extra. If nothing else, you can make paper airplanes out of them or something. Okay, so let's take a look at number 6. And I'll just say, I know people have been coming in and out. I'm videoing this one time through. And then I intend on going back and working more problems for people that have been coming in and that. So you can ask questions or we can go back through problems. I'm not going to record it again, but... Okay, so now we have... two brands of flares, and we're looking how long they burn. What kind of test? Two-sample t-test. There's two samples, and since we have standard deviations from sample, S's, it's t. I'm going to call this brand A and brand B, just to stick with my normal notation. So we know if brand A has a higher population mean than brand B, so HR mu A greater than mu B, and HO mu A equal to mu B, or mu A minus mu B equal to 0. The main reason I add this part on, that it's mu A minus mu B is equal to 0, is if I have to draw a sampling distribution. That way I know the center of the distribution is 0. And those are equivalent statements. I guess you can make a case for saying it either way anyway. But that's why I always make sure I get that one in there as well. Okay, so use the critical value approach. Okay, so before we can proceed, what do we need to do? What do we have to know before we can get the degrees of freedom? We need to know if we pool or not. Okay? So when you're doing the test between two means, early on in the game, maybe right away, you need to decide if you're going to pool or not. So I need squared values. So 1.4 squared, that's 1.96, isn't it? Someone check me on that, you know. And S squared B, 0.64. And one of those is more than twice the other. Okay? 1.96 is more than twice as large as 0.64. So do not pool. If they were about the same, we could pool, but they're quite a bit different, so we won't pool. So to get the degrees of freedom on the unpooled test, we pretty much just have to run the test through the calculator and get the degrees of freedom there. There is a formula. I think I gave it to you on one of the formula sheets. Let's just use the calculators on it. It's really not, there's nothing that much to be gained by that formula. So now if you would, go to your calculator and go to a two-sample t-test, stat test, two-sample t-test, and enter in the means, standard deviations, not the variance, enter the standard deviations and the sample sizes for both samples.
Sample, you would put this one, right?
Yeah, sample means 19.4. SX1 would be the 1.4,
Okay.
and then the N. Yeah, you're right. I just wanted to make sure you didn't put in the 1.96 and the 0.64. There's a tendency of people to do that.
We do not pool.
Right. Put no on the pooling and greater than in the hypothesis. And then it's going to give you a degrees of freedom when you get there. Does anybody have that? 52.5.
Yeah.
Always round this one down.
52.4.
So we're going to round that down to 52. So we're going to reject HO. If t-test is greater than, and now we'll go to our t-table and go to 52 degrees of freedom, 05, and a one-tailed test. And I've got 1.675. Just sort of as a side note, you know, you have the pooled and the unpooled tests. When you calculate the t-test value, they're going to be really close no matter which one. What changes is the degrees of freedom. See, in this one, the degrees of freedom is 52. If this were pooled, it would be 35 plus 40, that's 75 minus 2, or 73. And so it's the critical values in the table that really are more subject to change than the actual calculation. I mean, it makes a tiny difference, but not much. It's really the degrees of freedom that there's going to be a difference that means anything. It's going to be in the and the degrees of freedom related to the degrees of freedom rather than the calculation of the t-test. But the t-test is equal to the statistic, the difference between the two sample means, minus the hypothesized parameter. And I'm going to write this in here, but you really don't have to write this second part in. I like to just because it makes the same thing that we always do, statistic minus parameter. But that's always going to be 0 in that second part. And then divided by the standard error, which is the square root of S squared A over NA plus S squared B over NB. And if you want to, you can calculate that whole number off to the side before you do this. So X bar A minus X bar B is going to be 19.4 minus 15.1. And then we can divide by, this is going to be 1.96 divided by 35. Of course, taking the square root of all of this, and 0.64 divided by 40. So on the top, that's 4.3. Calculate just the bottom part now. We got about 0.268. And I got 16, is that right? 16.04. And if you really had things going a minute ago, you would have, when you calculated the degrees of freedom, you would have written this number down as a check figure. Okay. So anyway, 16.04, that is greater than 1.675. Therefore, we reject HO. And we conclude mu A is greater than mu B. So, questions about this one? Okay. Let's do some comparisons here. I'm going to leave this up here. Go back and look at problem 2. Problem 2 has two types of cars. We have 16 type A cars, 16 type B cars, two separate groups. Just like here, two separate groups, brand A and brand B. Okay. In this case, I've given you 16 values in one column and 16 in the other one. If this problem were like that, it would have 35 numbers in brand A and 40 in brand B. Okay. These are both difference between mean problems. Two separate groups. Do the means differ or in this case is mu A greater than mu B, and I think this one was also mu A greater than mu B. They both have two means. This one variance was more than twice the other. On this one, when we computed the standard deviations and then the variance, neither was twice the other, so we pooled. And in fact, when we went through the first time, just computing the thing before we computed standard deviations, I suggested that we pool on this one because the numbers were all in the same range right there. If one of the columns had numbers like 15 and 50 in it, I wouldn't have pooled because I would have thought they were more spread out than the other ones. So these two at least are by and large the same. They have different degrees of freedom because one of them, number 2, was pooled, and number 7 was unpooled. And then the other thing is that we worked it differently because we had the actual numbers here. Those of you who weren't here, we put one set of numbers in list 1, second set of numbers in list 2, and then we did 2 sample T interval, and then just referred to list 1 and list 2. Okay? Now compare that one, both of those, to number 4. Also 2 columns of numbers, but not like either of those 2 problems. This has 2 columns of numbers, but there's only 1 sample. This is a matched pairs test, and really what we have is x is equal to 5, 4, and so on, the differences. Then we computed the means and the standard deviations and did a 1 sample t-test on the differences.
So what type of problem is number 6?
Number 6 is a 2 sample t-test. Just 2 samples, and it has standard deviation, so it's a t-test. So both, I think it was 2 and 6 were both 2 sample t-tests. One of them was pooled and the other one wasn't. And number 4 is a matched pairs test.
So 2 is a 2 sample T.
Right. One of them was, we could have done a test with it. I change up from interval to p-value, so I don't have to ask that on every problem for every one of them. Okay, just kind of briefly going back through things, and then I'll turn the recorder off, and you guys can ask questions, or we can work problems again, or whatever. Number 3 groups, it's analysis of variance. Okay, 3 groups, it's analysis of variance. Anova, yes. Number 1, which should be an easy problem, but wasn't the first time through. In both A and B, it says find the probability. There are no hypotheses here, no p-values or anything like that. This is find the probability. So it tells you have a normal population, and then it has a mean and a standard deviation there, and it says find the value of such and such. Then in part B, it says now we've taken a sample size of 4, find the likelihood that a sample mean. Now what you have to do is, it's still going to be a bell curve. The mean is still going to be the same. It's going to be mu x bar, but it's going to equal the mean of the population. But the standard error is sigma x bar, and it's going to equal that population standard deviation divided by the square root of n. Okay? Then it's just a straight probability distribution. I'll work it again in a minute for those of you who weren't here. But I just want to, re-emphasize for folks that if it just says find the probability, it's none of the hypothesis testing or confidence intervals. It's just find the probability using the Z table. And I think the only other problems on there were just a 1 sample t-test, I think number 5. Okay. If you have trouble sleeping tonight,